Welcome to a series of lectures called Class, Selected Fundamentals, Basic Principles and Background Information. My name is Christian Roos. I'm professor at RWTH Aachen University and head of the chair of Glass and Glass Ceramic. This video series will deal with selected aspects of glass science and is intended to reinforce the content of the lectures. The video series are not based on a thematic sequence and structure of the lectures. This video is about the energy balance calculation in a glass furnace. Let's consider a Sankey diagram of a glass furnace. We have basically three important terms that apply. One is the actual energy that is required to melt the glass, H in. H in consists of the exploited heat, Hx, and the loss terms. The exploited heat is the energy that is theoretically needed to convert the raw materials into the glass. For the calculation of the exploited heat, please refer to the respective video. The loss terms are all the energy losses that can occur in a furnace. This can be the structural losses in the regenerator, the off-gas losses, and the structural losses in the furnace itself. The total equation that summarizes the energy need in a furnace is therefore the exploited heat plus the loss terms. And this equals the total energy that needs to put into the furnace to melt the glass. Now, the exploited heat is made up of the chemical heat requirement and of the sensible heat of the molten glass. The calculation of the exploited heat, as mentioned, is explained in another video. The principal equation is the chemical reaction enthalpy plus the sensible heat equals the exploited heat. The actual energy required to melt the glass, which is Hin, is a dependence of the efficiency eta x of the furnace and can be simply calculated by taking the exploited heat divided by the efficiency of the furnace. If the efficiency of the furnace is unknown, the actual energy required can be calculated via a combustion equation. In the simple example below, it is the combustion of methane with air. This yields CO2, water, and nitrogen. And if one knows the gas consumption of a furnace per day or per ton of glass, and the lower calorific value of the gas is known, Hin can be simply calculated. The loss terms in the furnace are a little bit more complex and more difficult to obtain. The sum of all loss terms from wall losses, radiation, flue gas losses, and from all the peripheral systems sum up to the total heat loss in the process. And as mentioned earlier, the loss terms plus the exploited heat equals the actual energy that needs to be brought into the furnace. As normally a large number of components contribute to the loss terms, in reality the loss terms normally needs to be measured with a quite great expense. And for the sake of simplification, in our example here, we take the loss terms as already known. Now let's have a look at a sample calculation. We assume the following glass data. The glass should have a chemical reaction enthalpy of 160 kilowatt-hours per ton of glass. The sensible heat demand of the glass at the respective temperature should be 420 kilowatt-hours per ton of glass. And the cullet content in the furnace should be 55%. This leads to an exploited heat of 492 kilowatt-hours per ton of glass, according to the previously shown equation. Now, the furnace data should be a heat loss amount of 708 kilowatt-hours per ton of glass. This leads, in relation to the exploited heat, to an efficiency of 41%, which is a reasonable efficiency of a fossil fuel-fired furnace. All this together with the calculation of the Hin in terms of Hin equals Hx divided by the efficiency of the furnace we end up at a total energy needed for melting 1 ton of glass of 1200 kilowatt hours per ton of glass. Now, the combustion data should be that we burn a gas in the furnace with a lower calorific value of 14 kilowatt hours per kilogram gas. By now calculating how much kilogram of gas at 14 kilowatt hour per kilogram calorific value is needed to supply the furnace with a total energy of 1200 kilowatt hours per ton of glass, yields that 85.7 kilogram gas per ton of glass are needed. So with this, a simple energy balance calculation of a furnace is done. And certainly you can do these calculations in basically all directions, meaning you also can take a certain amount of gas that you know is consumed by the furnace, and with that amount of gas calculate the actual energy demand of the furnace. With this, we are at the end of this video, and I trust it was helpful for your further understanding of glass science.